Hello, everyone, and welcome to another wonderful day of statistical mechanics. So today we're going to be focusing a little bit more on how to take the energies and partition functions we described for individual small molecule systems and how we can kind of scale these up into larger ensembles that we can use to describe the same sort of thermodynamic functions that we developed earlier in the semester. So one of the good places to start with this is to think of each of the individual partition functions describing the behavior of a small ideal system that has constant number of particles, volume, and energy. Now, part of the problem is that we really don't care so much about systems with constant energy, volume, or number of particles. Instead, what we often want to do is let some of these variables change while others may stay fixed in order to describe a larger system. Because remember, if I have constant energy, volume, and number of particles, then all I really have is a closed system, which is only so useful. However, it's going to be possible to allow for these systems to interact and exchange if we form an ensemble. So not just looking at one system, but say a group of 2, 4, 6, infinity number of linked identical systems. So depending on what sort of interchange you allow between these systems, that's going to dictate what kind of ensemble you're looking at. So the simplest form of ensemble is called the microcanonical ensemble. So in this case, each of my little subsystems acts as its own independent, isolated system. So no interaction is allowed between systems. So no energy interaction, no volume change, no particle exchange, none of it. So in this case, all I end up with is a total system with fixed N, V, and E, because it's going to have the same energy, volume, and number of particles that I say that it started with. And this is, again, only so useful. It's very good for closed systems, but we're only so interested in closed systems. So a much more popular choice, and the one we're going to focus in on, is called the canonical ensemble. So in this case, energy is allowed to move in between systems, but the volume of each system stays fixed, and so does the number of particles. So think of these as closed instead of isolated systems. So what this does is it gives my net ensemble a fixed number of particles, a fixed volume, and instead of a fixed energy, it gives me a fixed temperature. Now, this is really what we often care about, because we often let energy move in and out of systems, and by treating a fixed number of particles, this can help me derive molar properties. And so oftentimes, we're going to care very deeply about the canonical system. However, some people tend to care much more about particle exchange. So they want to see what happens to each of these systems as they grow and shrink. So one of the ways to do this is you still keep the volume fixed and you allow energy exchange, so the temperature becomes fixed. And instead of fixing the number of particles, what you do is you fix the chemical potential of each particle. So by fixed energy per particle, you're going to allow some of the energy to move in and out of the systems through this mode of chemical potential. So what we're going to do is we're going to focus specifically in this course on the canonical ensemble, as it's going to help us build up a lot of the thermodynamic functions that we care about. However, there are a number of graduate level courses that tend to focus in on the microcanonical, which is going to give us behaviors very similar to what we found for examining individual systems, as well as the grand canonical, which is very important when examining the behavior of a lot of processes such as phase change. But again, our focus is going to be placed on the canonical ensemble. So we're going to essentially build it from an imaginary collection of systems. So I'm going to have, say, n number of systems, which I'm going to define as 1, 2, 3, 4, and so on, or with the general state of I. So each of these systems can be found in a different state. So EI is going to be the energy of state I, and it's going to have a characteristic number of particles N, and a characteristic volume V. However, the entire ensemble is going to have slightly different variables. So it's going to have a total number of systems again, n. So this will be a little bit odd for me to describe verbally. But there's also going to be a total number of systems in state I. So I may have, so for example, I may have system 6 may have an energy of 0. It may be in the ground state, but it turns out so may systems 12, 15, and 18. And if I want to count how frequently I end up in that ground state, I'm going to need to make use of this n tilde I, focusing on the number of systems in state I. And instead of just focusing in on the energy of each state, I'm going to often want to characterize the total energy of the ensemble, as this is going to help drive a number of properties. And most notably, each possible ensemble is going to have its own characteristic weight as well. And not too surprisingly, we can define the weight or frequency of an ensemble with systems of certain energy and number of particles in the same way we defined the weight of individual systems, simply statistically describing it as the total number of, using the total number of systems in my ensemble times the number of systems in each individual state. So we'd expect a lot of states to be present in systems to be present in the ground state, while decreasing numbers in excited states, unless degeneracy kicks in, at which point the intermediate states can become more highly populated. So what we're going to want to specifically do is, just like we did with individual systems, we want to try and find the ensemble with the greatest weight, as it's going to tend to be the one that dominates the system. However, one of the things to note is that if all energies are equivalent, we're going to tend to find the ensemble with the greatest weight is going to be the one that occupies the most different energy levels. Because if I have the most if all my systems are in a different state, that's going to give my system a great deal of weight. Unfortunately, we also are going to have to apply the constraints of a fixed energy and a fixed number of systems, which is going to help drive a higher probability of finding the system with low energy states. And again, we can do this by generating a probability of finding a member of the ensemble in state I based on the number of states in state I over the total number of systems in the ensemble. So again, we're essentially treating the ensemble the same way we did individual systems, just kind of scaling it up. And again, similarly, what we can then do is predict this probability based on the energy of state I using an exponential function, and then essentially normalizing with the ensemble partition, the canonical ensemble partition quotient, where function, where here uppercase Q demonstrates the canonical ensemble partition function, whereas lowercase q represents the molecular partition function. And again, we can get the canonical ensemble partition function simply by summing up over the energy of each individual system. So using this canonical partition function and our probability expression, we can essentially try and determine the probability of finding a state function, the ensemble in state I. So again, finding it with a given structure. But what we're going to tend to find is that the probability of being located in a state, according to our probability function, should decrease with energy. As the energy of the state goes up, each individual state becomes less and less populated. However, we run into the fact that as I increase in energy, most of our systems become increasingly degenerate. And we saw this with several systems like rotational cases, where we saw, say, an algebraic increase in the degeneracy of the system, while we saw an exponential decrease in the probability of occupying any individual state. So what this means that is in terms of the most occupied energy levels, they tend to be most occupied at these more intermediate levels. But again, it all depends on the degeneracy of our energy levels. But it isn't uncommon for these energy levels to even be exponentially populated, which it can really dictate what energy levels are the most probably occupied, though it is very much not uncommon for them to be intermediate energies. However, ignoring degeneracy for the moment, one of the things that we can try and do is derive a set of our canonical partition functions in terms of our individual or molecular partition functions. So it should make sense that, as we've seen before, partition functions tend to be separable into their components. So I can get the partition function for my entire system by simply multiplying the total number of systems present, where I end up with n systems in my ensemble. Now, the real advantage of trying to of deriving our canonical partition function is we can treat each of our individual molecules with its own molecular partition function. So what I can then generate is my ensemble partition function based on the molecular partition function to the n power, where n is the number of molecules in the system. In other words, n is quite large. However, this approach does assume that each of these partition coefficients is truly independent. So what this requires is that all of our molecules are distinguishable, such as atoms in a solid lattice, where I can point at an atom and say, I know who you are. And you're not that atom 4 atoms over, because they're all fixed in place. However, by the time you reach fluids, you point to an atom, and then 10 minutes later, you can't point to the exact atom because they all look the same. So if I have if the atoms are indistinguishable, such as if I'm in the gas phase or in a liquid, what we have to worry about is that our partition function ends up getting counted multiple times. If Q1 is in one state and Q2 is in a different state, I don't want to count essentially the same ensemble, but with just the order switched. And it turns out statistically, there's an easy way to correct for this. And it's more or less that you just divide your system based on n factorial. So essentially, the more particles in your system, the larger the correction. However, this does lead us into some slight issues when n starts becoming on the order of Avogadro's number, as that's going to play a little bit of an issue because I don't want to do 10 to the 23rd factorial. However, what we can do is note that in many cases, such as while trying to determine the energies of a canonical partition, there's some tricks we can use to simplify. So, for example, if I'm trying to determine the energy of my canonical partition function, what I can do is express this energy in the same general function that I did for my molecular partition function. It can be given as 1 over the partition function times the derivative of the partition function with respect to beta under constant volume, which again then can be rephrased as a derivative with respect to natural log of the partition of the ensemble partition function with respect to beta. Now, what we can then do is insert our expression for a distinguishable system where Q equals the canonical partition function equals the molecular partition function to the number of molecules present, which lets us then correct our energy and then make use of the beauty that is log functions, where I can bring the exponential power down in front. And by doing so, all I end up doing is regenerating my definition of a molecular partition function. So it turns out we can actually generate the mean energy for a canonical ensemble of n particles simply by taking the average energy of our molecular partition function times n. And I do want to emphasize, while this seems very logical that I can take the average energy times the number of particles to get my total energy, it turns out it's not always so easy when working with other ensembles, which is, again, one of the reasons why we like to work with a canonical ensemble. And it turns out, even if I'm dealing with indistinguishability, where I have to introduce this factor of n factorial, it's still not so bad. Because what I can then do is, using the power of logs, pull out the n factorial out in front of my natural log of q, and essentially just subtract out my natural log of n factorial. Well, it turns out my natural log of n factorial has no dependence on beta. So its derivative just goes to 0. And all I'm left with is the same exact energy as for a distinguishable system. So in this case, we actually get very lucky in that when trying to describe the energy of a distinguishable or indistinguishable ensemble, we still end up with the same energies. We won't always be so lucky, but it's something to look out for when dealing with a pesky equation. See if you can separate it out and cancel any unwanted terms. So next time, we're going to be trying to take our descriptions of the energy of a canonical ensemble and use it as a building block to get back our thermodynamic functions we started with. Next time, internal energy, entropy, enthalpy, and free energy. Until then, take care.